Hello, this is Stuart Williams. Today I'm going to talk to you about handling fluids and using DI water and measuring its conductivity and other fluid conductivities. And this is with respect to an introduction to microfluidics, and more specifically electrokinetic microfluidics. And this video will help those who are new to this area conduct experimentations in this field. So the topics that we're going to talk about today is DI water. DI stands for deionized water, the use of potassium chloride in our experiments, and also how to suspend and resuspend microparticles. So first is DI water. Not all DI water is the same. For example, we have a clean room downstairs that has a DI water source, and we also have another source upstairs in a bio lab that does it. So either, whatever the source may be, we usually get a big jug of DI water for the lab, and then we put it in a smaller jug for different experiments. And then we'll measure the electrical conductivity of this and monitor it. Now, deionized water, you have to be very careful with contamination because the salt on your skin, as well as the gas in the air, will increase the conductivity of your liquid over time. So when you measure it, you should put a date on it, on your sample, as well as your little sources here, and then be very careful. So if I were to open this and handle this, I would put gloves on and make sure that I don't contaminate. For example, don't double dip with a pipette. Be careful that the tip here, when the cap is removed, it's not touching other surfaces. So just be mindful of that. So you have your DI water source, and you want to measure its electrical conductivity. So we have 2 meters in our lab that can measure electrical conductivity. This one can measure small volumes. So in the case of DI water, or something you can put in a beaker, we're going to use the larger one, the larger meter that I'll get to here in a second. But if you only have small volumes, this one does a decent job. It has a source right there at the tip where you can put in your sample, and then before you take the measurement, you calibrate it, and then you get a measurement. Now, this instrumentation is not as accurate as this benchtop unit. So this benchtop unit, when you have this meter here, you want to make sure that that your liquid covers this whole cavity with liquid, so there's no air pockets inside of here. You cover the whole cavity, and then you measure the electrical conductivity using that meter. Now, DI water is fine, and technically there are ions within the DI water, but from a physicist perspective, we want to know the mobility of the ions, we want to have control of those ions, and we want to give the ions some majority. We want to give it some ions that we know, and that's why we use potassium chloride within our experiments. So why we use that, and I'll bring this here, is that if you look at the table on the right, and this is from a textbook, AC Electrokinetics, Colloids, and Nanoparticles. So if you look at the table on the right, you can see the ion mobility for potassium and chloride are close to each other. So when you have an AC signal for your electrokinetic experiments, the positive and negative ions should move at a relatively similar rate. And there's other studies that have shown that different ions might give different responses, especially at low AC frequencies. But those are different studies that you can look up. But also, let's look at the conductivity. So the conductivity has a linear relationship with respect to the, now these are on log scales. So I said linear, but here it's a log graph of the molar concentration of one and the conductivity of the other. So if you have a solution and you want to dilute it to try to reach a target conductivity, it's rather straightforward to do so. So with those, we've covered DI water. We've also measured why we use potassium chloride. And the next thing we're going to talk about is what if you have a suspension of particles and you want it at a particular fluid conductivity. So first, you make the fluid conductivity, and then you get a centrifuge. Now we have a small centrifuge here, but you may have access to larger ones. So you would take your particles and then you suspend them in the liquid that you want. And then technically the particles come, a lot of particles come in their own liquid suspension. So you might commercially purchase it, and it may be suspended in some liquid suspension, but you want to suspend it in your own liquid. You want to suspend it in your own conductivity, because you don't know what the conductivity is of the supplier, or you just want to rinse it off completely. And that's what we're going to do here. So you would suspend your particles in here, and then you would centrifuge it until the particles create a pellet at the bottom, and then you would use a pipette to suck out all of the liquid except for the pellet that remains, as much as you can without disturbing the pellet. Suck out all the liquid, and then you add liquid back to that sample of the liquid that you have created, the liquid that you want to use. So then you would resuspend it, the pellet, adding the liquid that you want, mix it around, and then you centrifuge it again. You centrifuge it again, concentrating the pellet. Then you remove the liquid, the excess liquid, keeping the pellet in place. You remove the excess liquid, and then you add the liquid that you want again. Do it 3 times. So once after that third time, that third suspension, you feel confident that the particles that you have are suspended in the liquid media conductivity that you created. Now, microparticles can be suspended. Some nanoparticles, but not a lot. You're going to have some specialized equipment like an ultracentrifuge or others. So when we use microparticles, this is a straightforward way of suspending the microparticles into a liquid conductivity that we want. So that covers the topics we wanted to cover in this video. So thank you for your attention. If you have any questions, feel free to contact me at the address here.